that we want to apply the work energy theorem to a spring system. So here we go. So we know that the spring force is clearly a variable force. Okay? So clearly, the spring force is a variable force. Now, why do I say that? Because check it out. The spring force is proportional to minus kx. X is a variable. What does this mean? Well, what this means here is that, you know, all those wonderful kinematic equations that we used before, we can't use them anymore. So those kinematic equations from chapters 2 and 4 to understand motion are not valid anymore. You can't use them. The only way you can use Newton's laws, so using Newton's second law requires solving second order differential equations. And that at Cabrillo, if I remember correctly with my numbers, it's math 7. That is not a prerequisite, you know, for this course. So it's beyond the scope of this course if we tried to use Newton's second law. But there's hope. And the hope is that at this level, we can use the work energy theorem to understand motion of, motion when a variable force does work. We don't have to use differential equations. And that is freaking awesome. Okay? That is really awesome. So what we want to do here is that, one, we're going to be dealing with pictures, not differential equations. And pictures, just like I showed you earlier when we were looking at the example with the caver. I mean, come on. If you can get the picture right, you know how to solve the problem. So the picture here becomes just as important as with Newton's second law here. So let's go look at this thing here. So what I want to do here is that I want to do the exact same thing. Okay? I want to do the exact same thing as we did before, but now I want to go through the details and sort of like write the language. Here I go. So I'm going to break this up into cases here. I'm going to break it up where the cart is going to move away from the equilibrium to the right, and then it's going to stop. And then I'm going to look at motion going back towards the equilibrium. That's going to be case 2. So the left, going to the left is the same as going to the right. So here we go. Let's go look at this thing here. So note, I'm spending a lot of time on the spring force because this is an important force in physics. It shows up even when I was teaching physics 4D last semester, we were modeling how atoms behave in terms of the spring force because the actual equations were too difficult to solve. So here I go. So I'm going to set up two cases. So there's going to be case number one. And what we're going to do here is that we're going to have a cart moving to the right away from the equilibrium. And then I want to look at the return trip, which I'll call case number two. Now I'm having the cart moving towards the equilibrium. And what changes when that happens? And that's what we want to look at right now. So here we go. So here's case number one. And this is cart moving away from equilibrium. So what I want to do here is that I want to set up a series of carts here. Okay, so I want to do what we did last time. So I want to set it up. And I want to do it a couple of times. So let's say, let's see, make sure that I have plenty of space. So I have this situation. So here's my cart now. So if I look at this thing, here's going to be my equilibrium point right here. Right? So my equilibrium point is going to be right here. So here's X equilibrium. So now I need to go in and draw my cart. So what I'm seeing here is that my cart is doing what? It's moving at the origin, then it moves to here, and then it's going to move all the way to here. And you know what I'm going to do? I'm going to stretch this out just a tiny bit, just so that I have a little bit more space. Okay. So what you're seeing here is as the cart moves, the question that we're asking, what are the springs doing now? Well, at the origin, what I do know is that it's moving right here like this. So this is the speed right here. Now I want to be careful here. So at the equilibrium point, we know that we have a spring here, but now look at the spring. It's stretched out more. And then here, it's really, really, really stretched out. So what you're seeing here is that the spring pulling it to the left, this tells me here is that right here at the equilibrium, I must have maximum speed. Why? The spring force is zero. It's not acting on it. But as I move this way, the spring force is slowing down the cart. And when it gets to its stopping point, the speed is zero. Now, how can I say that? Well, look at the spring force. Here, there's no negative spring that's working on the cart. But now, what's happening? There's a spring force that's in the opposite direction. So it's got to be working to reduce its kinetic energy. And when it gets to the point where it stops, that means I'm farther from the equilibrium, so I should have maximum spring force at that point. So if I look at my springs, yeah, I have these other springs, and what I'm really looking at is I'm looking at the net spring force. But here I go. Look at my displacement. My displacement is in that direction, and then here, this distance here is then the maximum displacement possible where that car stops here. So at this point here, what we should be saying here is that I should be highlighting a couple of things here. So what I said here is that the spring force increases as cart moves farther away from x equilibrium, which we knew that, but I'm trying to draw that explicitly here. And what you're seeing here is that there's some language that we have to talk about. So what you're going to find here is that where the cart stops, it stops momentarily, okay? Okay, it stops momentarily. We call this the turning point. Okay, so that means this point right here, this is what we call the turning point. So X turn. And what it's doing here is that it's changing directions. So the turning point implies that it's changing directions from right to left now. That's what we mean by the turning point. But it's at rest at that point because its speed is 0. Okay, the maximum displacement from equilibrium is called the amplitude. So the amplitude is that maximum displacement. And then the other thing that we find here is that when F spring is max, so then from N to L, that tells us that we have maximum acceleration. So even though the object is at rest, okay, we got to be careful with their language here. Even if the cart is at rest at the turning point, it has maximum acceleration. Because Newton's second law says that the net force is proportional to the acceleration. So I can have 0 speed and, maximum acceleration. So then what we want to do here is that we want to go in and look at what this thing looks graphically. Okay, so now here we go. So the question is, what does this look like graphically? Because that's what we're interested in. We want to calculate the work, right? And the reason why we're asking this is that we know that the work is what? It's the area under the curve. That's what we're interested in. because that's how we calculate the change in kinetic energy. We're applying the work energy theorem to the spring system now. And when we apply it to the spring system, what we're going to be looking at here is that we're going to be trying to do the same thing that we did with kinetic energy. And what do I mean by that? Well, when we applied the work energy theorem to kinetic energy, what we did here is that we took a work and we changed, and in this case, the speed of a car. So the energy that was stored by doing that work is what we called kinetic energy. So kinetic energy is stored energy. Now we want to apply the work energy theorem to the spring mass system. And what we're going to do here is that we're going to learn about a new kind of energy or a new form of energy. And you'll see here is that this spring energy is connected to position, really changes in position, just like kinetic energy is associated with changes in velocity. And we started looking at one of the cases, but we want to look at two cases. Is we want to look at the cart that moves away from the equilibrium, and then we want to look at the cart that moves towards equilibrium. Those are two different situations. And the reason why they're different is that one of them is moving away from the equilibrium. So you're stretching the spring, and then you're doing negative work. And now, as you move towards equilibrium, you're speeding up and you're doing positive work. And so what we did here is that we went in and we started looking at this. I said, here's the case one. We imagined that I said that because the net force is 0 at the equilibrium, that's going to be the maximum speed as a car moves from the left to the right. But as soon as I pass the equilibrium point, remember the equilibrium point is our 0 point, then the spring force is doing negative work and it's slowing the car down. And as the car continues to move as far as it can to the right, essentially when the kinetic energy is now opposite of the work done by the spring, then at the point that it stopped, we said that this was maximum force being applied here. So really quickly here, we said that the spring force increases because it's dependent upon position. The farther we are from the equilibrium point, the more work is done. When the car stops, it stops momentarily. That's what we call the turning point. That's where you're getting a change in direction. Maximum displacement from the equilibrium is called the amplitude. So that's just a language thing. And when a car stops, the spring force is maximal, which then from Newton's second law tells us that it's maximal acceleration, and that occurs at the turning point. And so what's contradictory to a lot of people here is that they say, when the car comes to rest, its speed is 0. That's where the velocity is changing directions. That is the location of maximum acceleration. So what you're finding here is that some people find it unusual because this is, how could something be at rest and have maximal acceleration? Well, then that means that you're mixing up velocity and acceleration. They're two different things. So what we want to do here is that even though I'm jumping the gun, I want to go in and I want to keep using the energy picture so it becomes intuitive. And you're going to see that we're going to draw this here very shortly here. Look at what happens to the cart. So you could imagine that the cart is starting over here to the left, right? It's starting over here to the left and it's moving down. So as it moves down, you could imagine that clearly at the bottom of the well, the spring well, what you're seeing here is that the car must be traveling now with its maximum speed. And you may say, well, in this picture right here, you get maximum work before the work change is positive as it goes down. And then at the bottom, of course, it goes faster. You know that when you're riding a bike. So now it starts to climb up the hill. and it can only go up so high. And at the point where it stops, that's what we call the turning point. And then, of course, it's going to come back. So what we did here is that we only looked going from the equilibrium to the turning point. So the next piece that we're going to look at is that we're going to be going all the way back down. That's going to be case 2. But we're not done with case 1. And so when you look at case 1, what we got to do here is that if we're going to look at this thing graphically, we have to use the work energy theorem. Why do we have to use the work energy theorem? Well, this is a variable force. That means that you have to solve a second order differential equation, which is beyond the scope of this course. Lucky for us, we have the work energy theorem that allows us to deal with variable forces. And so what we're looking at here is that we know that the work is the area underneath the curve. So let's check it out. And so what we're seeing here is the spring force is a linear force. It's minus kx here. And I'm going to plot the horizontal distance x. So that spring force is a negative force. So I have to draw that negative slope from the equilibrium point down here. So what I'm going to do here is that you could see that what I'm going to do is that I'm just going to draw a line from the equilibrium, and it's going to come in and it's going to look something like this here. So I want to go to about right here. Is that where I want to go? Yeah, let's say. So let's say that I draw to right there. So what I'm really doing here is that I'm moving to where? This point right here is my what? My turning point. That's where I'm going to turn around. So what you're seeing here is that as the cart, look at the picture here, as the cart is moving to the right, note that the displacement and the spring force are in opposite direction, so it does negative work. So here I go. I'm going to come in, and I'm going to highlight this whole thing. This is the work of the spring. The spring is doing negative work. So when I'm looking at this, in this scenario here, this is the work of the spring, and it's negative work. So once again, here's my cart. It's moving in that direction. So when I'm looking at it, what I'm seeing here is that the displacement is in this direction, but the spring force is in that direction. That's what tells me that I'm having a spring force that's negative. So now we know that we're going to get a negative number. Of course we're going to get a negative number. We expected that because the cart is slowing down. So here we go. So here I go. So now let's write the work. The work then is going to be what? It's going to be the force dotted with the displacement. And this is a definite integral. So I'm going to go from the equilibrium point to the turning point. Now, because this is along the x direction, this line integral can now be an integral along just the x direction. And so what you find here is that this is then going to be the integral of what? Of these two limits. And then it's the spring force times dx. So now if I integrate this, you all know that this guy's going to be here with k being a constant. This is going to be 1/2 x squared of the turning minus 1/2 x squared of the equilibrium point. Now, I know that the equilibrium point is 0. but I'm just making it into a definite integral. Now, it turns out that I am missing a sign here. I mean, it's there, but I want to really stress it, is that there's that negative value here. And what you're seeing here is that when you look at this, this is a term that shows up quite a bit. And anytime you deal with the spring, what you're getting here is that there's a minus sign here, and I'm getting a term that reads 1/2 k x term, squared minus 1/2 k x equilibrium squared. And if you make some analogy with this here, this looks very similar to the work equal to the change in kinetic energy. Because when we did this, we had 1/2 mv2 squared minus 1/2 mv1 squared. And what we said here is that because this term shows up so much, we then define it as the kinetic energy term. Well, it turns out that this term also shows up quite a bit, and this is the energy, or this is the spring energy. How do I say that? This is associated with the work stored into the spring. And we call this, of course, spring energy. And in the next chapter, we're going to define this as spring potential energy. But in this chapter, we're not supposed to do that because we haven't talked about the difference between these two. But what I want to show you, that there is a big difference. Okay? There is a really big difference. And believe it or not, the big difference is that this is a plus sign. This is a negative sign. And it turns out that anytime you have a negative sign like that, that has a very, very specific meaning here. So this is then the energy stored in a spring. And it's that minus sign that will be a central point very early on the chapter to figure out what that meaning of the minus sign is here. But for right now, this is what we say here. Okay, so let's be very, very clear so that we know exactly what we mean. So here's what we're saying here. So in summary, we have the work of the spring is then going to be minus 1/2 k x2 squared minus 1/2 k x1 squared. Okay. And what do I say? What have I been stressing again and again and again? This thing is what? Meaningful. Why is it meaningful? Because this represents a change in energy. In this case, it's the change in the spring energy. So when somebody goes in and they say, okay, what's the energy of the spring? And somebody's going to come in and they're going to write, oh yeah, it's 1/2 k x squared. You know exactly what I'm going to say. I'm going to say that this statement is what? Meaning less. Because think about it. In order to do work, you have to go from one location to the other. So to say that the work at one point is meaningful, well, that's hogwash. So let's get back to our problem here. So now I want to go back to the force versus distance plot. And what we're seeing here is that the equilibrium point is 0. So if I come in and I look at this thing, you could see here that the work of the spring is then going to be what? There's my minus sign. Then I'm going to get 1/2 k x at the turning point squared minus 1/2 k x equilibrium squared. But wait a minute, this guy is 0. And because that is 0, you're seeing that this is minus 1/2 k x of the turning point plus 0. And you can see that this guy is what? Negative. Right, that this guy is less than 0, which implies that it's negative, and that's exactly what we expected, because negative means that there's negative work. So therefore, this implies here is that the speed, right? So that what this tells us here is that the work of the spring being negative tells us that the kinetic energy of the cart is slowing down. Exactly what we expected from the work energy term. So that's what that relationship tells us, that the energy of the spring is related to the work.